Now let's consider other types of ion selective electrodes. Okay, ion selective electrodes are very important for the practical purpose. They are widely used in clinical the purpose, because they are uh, very fast responding, to the analyte. Okay, now let's assume now a very serious patient is brought into the intensive care unit, and then doctors must take steps to to take care of him. Yeah, but to do that, the doctors need basic informations. Okay, for the patient. Yeah. So for the purpose, ion selective electrodes may be used to measure, for example, the potassium ion concentration, and glucose, and dose. Okay. Yeah. But ordinarily, if the situation is not that serious, then take the blood, and then the for several days, um, all the analysis can be done. But in a case of emergency, the rapid and accurate measurement is very important. Yeah. So for doctor to make a diagnosis for a critically ill patient, okay, need blood into hospital lab can be measured by electrochemical method like ISE. Okay, so this table shows some the ISE for certain the ions and certain molecules. Okay, yeah. Potassium and calcium ion concentration is important, and here glucose. Yeah, well, the glucose cannot be measured by ion selective electrode by other means. Yeah, you will see in the next chapter how to monitor glucose level. Okay, and here CO2. CO2 is not an ion, but you can use glass electrode to measure CO2. Yeah, you'll see soon. Okay. Okay, types of ion selective electrodes. Yeah, first one, glass membranes for proton concentration and metal ions. Okay, yeah, we've already considered in detail the glass electrode and solid state electrode based on inorganic salt crystal. Okay, and you'll see, shortly. And liquid based electrode using hydrophobic polymer membrane saturated with liquid ion exchange called ionophore. Okay, and lastly, the compound electrode with a species selective electrode enclosed by a membrane which can separate the species. Okay, let's consider one by one from number two. Okay, well, first, before we take a look at the types of electrodes, now let's consider selectivity coefficient. Actually, ion selective electrodes not responding only one species, but it may respond to other, several other, ions. Okay. For example, the for the pH measurement, usually people use glass electrode. Yeah, but as I mentioned, at the higher pH, the glass membrane, of course, respond to protons, but also it respond to sodium ions. Okay, when the proton concentration is too low, right? And then glass membrane may respond to other ions. So you have to consider how the sodium ions affect pH measurement. Okay, so so we can introduce the selectivity coefficient. Okay, it is defined by this equation. The symbol for the selectivity coefficient is K. So A, comma X. Yeah? This is defined by respond to X divided by respond to A. Here, where the X is the interfering species and A is the species of your interest. Okay, so this means Kax is not the zero. It is zero if that electrode only respond to A and respond to X is zero, right? But that's not the case. Okay? So, by defining a selectivity coefficient this way, and then we have to rewrite the Nernst equation. Okay, here is an example. Potassium ion selective electrode, yeah? The valinomycin. This is a very famous ionophore for measuring potassium ion. But not only potassium ion, valinomycin also responds to sodium ion. Yeah, but selectivity coefficient here is 10 to minus 5. Okay, very small. This is very good. This means that uh, uh, when sodium ions are 100,000 and potassium ion is only one, that the response is the same. Okay, and also the valinomycin responds to cesium ion, yeah, and then selectivity coefficient is 0.44. Wow, very large. Okay, but there is the cesium ion is not a common ion. Okay, so that case is quite rare. Okay, so in most cases we don't have to worry about the presence of a cesium ion. Likewise, the rubidium ion, valinomycin is more selective to rubidium ion than potassium ion. Again, rubidium ion is not a common ion. Okay, there is a very little chance to have rubidium ion in your solution. Okay, but be careful. Okay, so the ion selective electrode response this equation can be modified, okay, to take this one, this is selectivity coefficient. Okay, let's assume that A ion is your ion of interest. Okay, and then there are many interfering ions. Okay, not only one, there are many, two or three or maybe 10, no? 10 ions are interfering your measurement, and then every ion interference that factor should be added here. Okay, and then this logarithm term can be written okay, a activity of A and plus the summation of all other ions contribution here. Okay, quite simple. Yeah, here is an example. You have a fluoride ion selective electrode, yeah, and hydroxide ion is one of the most interfering species, and people already measured selectivity coefficient for hydroxide ion with respect to fluoride ion is 0.1. Okay, the question is, what is potential change when 10 to minus 4 molar fluoride ion at pH 5.5 is raised to pH 10 to 5? Okay, now you understand, right? Potential may change, okay, when the pH changes from 5.5 to 10.5 at a constant fluoride concentration of 10 to minus 4 molar, right? So from this selectivity coefficient at higher pH, proton hydrox concentration becomes also very high, so it may affect fluoride ion concentration calculation. Okay, 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 let's solve. Let's consider at pH 5.5. In this pH, hydroxide ion concentration is what? 10 to minus 14 minus 5.5 is 8.5. 10 to minus 8.5. So at this pH, hydroxide ion concentration is negligible, negligibly small. So we don't need to consider it is interfering factor here. Okay, so we simply write E equals constant and minus Y fluoride ion has a negative sign, minus 1. Okay, and 0.05916 multiplied by logarithm of this concentration, and then it gives constant plus 236.6 millivolt. Okay, and now let's consider the at pH is 10.5. Okay, at this pH increased by 5, and then hydroxide ion concentration becomes 3.2 times 10 to minus 4 molar. Okay, and again we write the next equation. E equals constant minus this value multiplied by logarithm of this one, and plus selectivity coefficient 0.1 times 10 to minus 3.2 times 10 to minus 4. Okay, this part cannot be ignored anymore, and then you get E equals constant plus 229.5 millivolt. Okay, wow. No, since that is the fluoride concentration, and as long as fluoride ion concentration is constant, and then the potential must be constant, but because of interfering effect of hydroxide ion, it changes. Okay, by how much? By 7.1 millivolt. Okay, yeah, this difference this difference is not small. Okay, so you have to consider this difference. Okay, how ISE work? Unlike ion equilibrate with the ion exchange site at outer surface of membrane, diffusion of unalloyed ion change charge induces charge imbalance across the interface. Charge change in unalloyed ion concentration makes potential difference. Okay, and in this simple example, we know that it is important to consider interfering species. Okay, yeah. Okay, let's first consider solid state based ion selective electrode. Okay, here this one lanthanum fluoride. Yeah, this one when it is doped with europium fluoride, it is sensitive to fluoride ion. Okay, this is inorganic crystal lanthanum fluoride. Okay, and then the lanthanum has 3 arms. Okay, but when it is doped with europium fluoride, europium, this ion has 2 arms. Okay, so there will be a vacancy in lanthanum fluoride crystal. Okay, because of europium, doped europium here. Okay, and since this vacancy, yeah, is moving, yeah, this one actually this frequency is for fluoride ion, and here, and then since this is vacant, and then this fluoride ion moves inside the lanthanum fluoride crystal. Okay, the structure of the electrode is quite simple. You take the this type of tube, and here you open this tube and you insert inorganic crystal. Okay, and inside you put the silver chloride reference electrode, and solution must contain fluoride ion. Okay, since uh, you want to measure fluoride ion, so internal solution also should contain fluoride ion. Okay, so here fluoride ion can jump into frequency through the lattice and diffuse from one side to the other side. Okay, so this fluoride ion selective electrode is very useful. Okay, control of fluoridation of municipal water supplies. Okay, yeah. So using this electrode, you can measure fluoride ion concentration very rapidly. Okay, and what is the response equation? E equals constant minus beta. Yeah, beta is always there, and this one 0.05916 multiplied by logarithm of fluoride activity. Okay, at low pH, fluoride ion converts HF. Okay, You see, HF is also weak acid, so at low pH there is a higher concentration of proton. So the fluoride ion, some of them exist in the form of HF, yeah, because pKa equals 3.7. ISE is insensitive. In that case, in the presence of hydrogen fluoride, this ion selective electrode doesn't respond to fluoride ion very well. Yeah. But here the only interfering species is hydroxide ion, as we considered this example. Okay, only hydroxide ion is the interfering species, and selectivity coefficient is 0.1. Usually used concentrated, uh, uh, usually used condition at pH 5.5. Okay, in this pH, since hydroxide ion concentration is quite low, so there is no interference effect. Okay, and keep all standard unknown at a constant ionic strength. We rewrite, let me say, this equation using a concentration and activity coefficient. Okay, and activity coefficient is constant at a constant what ionic strength. Okay, and then this part is constant, and the potential is only uh, depends on fluoride ion concentration, not activity. Okay, and this figure shows that uh, uh, this electrode gives a very wide linear range from 0 to -6, around the 6th order of magnitude. Okay, very good actually. Yeah, here is an example. For the standard solution you prepare, maintained at a constant ion strength with 0.1 molar sodium nitrate. Okay, and then you change the fluoride ion concentration under the same ion strength, and then you measure the electrode potential at a concentration of 1.0 times 10 to the minus 5 molar. You measured E equals 100 exactly, and at 0.1 millimolar fluoride ion, then E becomes 41.5, and at 1 millimolar concentration, E equals minus 17.0 millivolt. Okay, yeah. And uh, what is the question? And we write it this way. Okay, uh, what is the fluoride concentration at a potential of 0 volt? Okay, and this equation can be written uh, in this form: E equals m logarithm of fluoride ion plus p. Okay, this is the uh, one first order equation. Yeah, and it is a straight line. It should give a straight line. And now plot the fluoride ion concentration, log of fluoride concentration in x-axis, and the y-axis is potential, and then you get this slope and what this intercept. Okay, and here is a result. The straight line slope is minus 58.5 millivolt, and y-intercept is minus 192.5 millivolt here. Okay, and now we solve for E equals 0. Okay, and then for the ion concentration is 5.1 times 10 to the minus 4 molar. Okay, quite easy. All right, another solid state ion selective electrode are developed, especially using this one, silver, this anion, this solid. Okay, with for example, for the detection of fluoride ion, the lanthanum fluoride crystal may be used, but for chloride ion detection, silver chloride based electrode is used. Okay, for bromide ion, silver bromide is used. For iodide and silver iodide, thiocyanate and silver thiocyanate, yeah, and cyanide ion, you can use silver iodide crystal. Okay, for sulfide ion, you can use silver sulfide. Okay, yeah. Okay, let me introduce a very special case in which cadmium sulfide crystal respond to this one, uh, hydrogen sulfide ion. Okay, and this is the structure of cadmium sulfide. Okay, so if you cleave surface, you know, cadmium plane or sulfur plane can be exposed. Okay, when you cut this cadmium sulfide with a razor blade. Okay, and since cadmium sulfide it shows cadmium plane or sulfur plane, so this cadmium sulfide crystal respond to this one hydrogen sulfide and also to respond to let me see, yeah, yeah, right, the cadmium, this one, this is hydrogen sulfide. Okay, but depending on which surface is exposed, response is different. Okay, when sulfur plane is exposed, this one sulfur, and then this potential change with respect to hydrogen sulfide concentration change, this change is not big. Okay, but when cadmium surface is exposed, it is very sensitive to hydrogen sulfide ion here. Okay, yeah. The steep slope is more desirable. Okay, more strongly respond. Okay, let's stop here.